Let's optimize some JavaScript. Hey, today we're going to be doing a deep dive on optimizing a chunk of JavaScript code. Specifically, I have a fairly unoptimized class that we've built up in a previous tutorial. We left a lot of performance on the table in the interest of making it easy to understand and readable. Today we're walking through and I'll be showing you how to profile and optimize this, ending up with something significantly faster. Now, whether you're interested in game-specific optimization or just general JavaScript optimization, I think you'll learn and pick up a few tips today. Anyway, so leading off from the last tutorial, we covered the basic implementation of a spatial hash grid, which can be super useful in game situations. And given it's such a simple and easy data structure to implement, it lends itself really well to profiling and optimization. Before we go, make sure you're subscribed so you don't miss out on future videos. So let's get started. My rough strategy is to start with some high-level questions about the code and gradually refine them. Usually, you start with some questions like, is this, whatever it is it having a real tangible effect on your code? Is this actually important to spend time optimizing? I'm not usually the type to start optimizing something right away, so you need to prove that it's a problem first. Next, you want to try and isolate the code you're optimizing into a benchmark of some sort, or at least a reproducible situation, to create a baseline to optimize against. In games, this might either be by actually creating a real benchmark by running the code in an isolated situation, or by using a scenario that's at least consistent. In our case, I created a synthetic little benchmark comparing the results of thousands of find nearby or update calls. After that, you want to examine the code in question and ask some general questions. Things like, can this code run realistically faster? If so, and if the stars were aligned, the moon's in the right position, whatever, roughly, how fast could it go? What's the upper bound here? The speed of light, the fastest you can go without resorting to magic. This is an important question because there's an absolute bottom line of work that a bit of code has to do, despite any and all optimizations, and if you estimate that things still won't go fast enough, it's time to step back and think about optimizing at a higher level. The example that's usually thrown around is that one pregnant woman can produce a baby in roughly 9 months, but 9 pregnant women can't produce a baby in 1 month. Let's dive into the code. The very first thing I'm going to do is take the original spatial grid slow class and copy-paste it into a new class. The reason is that I want to be able to do A/B tests and compare the performance directly between the old and new code, given the exact same inputs. Now that's out of the way, let's take a quick tour of the benchmark code. There's not much to explain here other than we generate a bunch of client data and we use this grid tester class to batch a large number of calls to find nearby or update. Let's make sure there's actually enough work to profile, so let's bump up the numbers to like 10,000, meaning we'll do 10,000 queries per benchmark run. This is just to make it easier to gauge the results of profiling. Next, we'll grab a profile. So, if you didn't know, Chrome has a built-in profiler. You just need to bring up DevTools, so you just go press this little icon here. I think it's called a hamburger icon. I'm not sure. Go to More Tools, and then you can open up Developer Tools. You can also just press Ctrl-Shift-C to bring it up with a keyboard shortcut. You should see a bunch of tabs here. We're going to use the Performance tab, so I'll just click on that. At first, it's pretty empty. We have to actually record a profile. There's 2 buttons to take profiles. There's the record button, which just sort of starts profiling right away. The other is a bit of a convenience one. What it does is starts profiling and then reloads the page for you. And I'll use that since the benchmark I wrote just runs as soon as the page loads. So after you press the button here, I just need to wait a few seconds and then I can hit stop. It'll process things for a second, and then you'll get this timeline view of the main thread as well as other threads, and you can see the dependencies and IPCs between processes. If you press the Sources tab, you'll get this cool breakdown of how much time was attributed to individual lines of code, which is mostly what I'll be using today. So let's kind of browse through a bit, and we can roughly see where time is getting spent. There's a little bit of time getting lost in some unnecessary stuff, like destructuring, like on these lines. We're spending a bit of time here and there, but overall, it's pretty obvious that we're sinking most of our time into the big calls. I don't really like killing these tiny things anyway, because they make things nice and readable, which is important because when there's bigger fish to fry, trying to go after these is really scraping the bottom of the barrel. There's a time and place for those kind of micro optimizations, but it's not now. Anyway, let's take a deeper look at a few of these lines, specifically clients.add and delete. And we should understand what these are and why they're slow. The clients and cells, these are either set containers or map containers, both of which are, depending on the implementation, going to be order log n or order 1 time complexity for things like access. So, reasonably fast. A couple observations right off the bat. We're taking a ton of time in just a few spots, those being the set, add, and deletes. Now there's two major hotspots. The first is in find nearby, where the results is a set. You can see it's declared down here, and we add to it over on this line. Now the reason for this is simple. Units can be inserted into multiple cells. Recall back to the first video, if you have a large unit that spans multiple cells, it gets inserted into multiple cells, which is simple enough. But it has this side effect that when you retrieve the client from multiple cells, there's a chance of duplicates. The strength of a set container is that it guarantees that all the elements in the container are unique, which in this case is great because that means we can just add every client from every cell and the set will take care of making sure that we don't have any duplicates. But there's a slight downside in that it's not as fast as it could be, which is pretty obvious from the profile. Internally, the set container will be implemented either with some sort of tree or a hash table, meaning operations will be sublinear. If it's a tree, it's probably a red-black tree, and so insertion will be something like order log n, and if it's a hash table, then insertion will be amortized order 1. This is a long way of saying they're fast, but when you're doing these calls hundreds or thousands of times per frame, they're not fast enough. So what is fast enough? Or I guess the better question is, if we wanted to do this as fast as possible, what would it look like? Well, fast as possible, assuming we still want to put together a list to be returned, would be to return an array. The only problem is that we still need to deduplicate the items in there so we don't return the same client multiple times. A set was kind of overkill to do this because we know that each client is uniquely allocated anyway, meaning whoever calls new client expects to get a brand new, unique client every single call. So we're going to make some small changes here so that we can ensure that we get no duplicates in the list, but at almost zero cost. So what we can do is scroll up to new client and make a small change to the client definition. What we're doing in here is we're adding a new field called query ID, and we're going to default this to -1 to start. Next, we need to go up to the constructor and declare a new member property. We're calling it this.queryIDs and just initialize it to 0 to begin with. We're going to be using this to deduplicate clients in the find nearby function, so let's scroll down there and put it to use. The first thing we'll do is change the results set into an array, since appending to an array is about as cheap as it gets, and we're going to be using the query ID property that we just added to remove duplicates. Next, we're going to increment the query ID right here before the main loop. This ensures that the query ID we're using in this call is unique. Then, while we're iterating the list of clients within an individual cell, what we can do is check the client's query ID versus the current query ID. If it's different, it means that we haven't seen this client yet, so go ahead and add it to the results array. By the way, since the results array isn't a set anymore, we need to switch from add to push. Then we need to make sure to set this client's query ID to the current query ID, and that means if it turns up in another cell, this if statement will fail and it won't be added to the list. And so we're good. This little change gets rid of the set container we were using for the results, and let's compare the performance. And we're seeing a considerable improvement here. The slow grid find nearby calls took roughly around 107 milliseconds or so, but the new improved one only took about 44. Looks like it's roughly 2 times faster. But there's still a lot of low-hanging fruit in the function, so let's go back. First thing we can do is take a new profile, so go ahead and press the second profiling button here, which starts profiling and reloads the page. A few seconds should be good, and then we can stop the capture and take a look. I'm going to go straight to the source tab this time, since I want to see how hotspots in find nearby changed. We're still losing a lot of time in here, and the biggest thing to notice is that a lot of it is just going to iterating over the values in the cell and checking if the cell even exists. Those two add up to quite a few milliseconds, and there's not a whole lot of reason for this. The check to see if the cell exists is just because we lazily created them. If we didn't lazily create each cell, we'd know for certain it exists. And iterating the values in the set, well, that's never going to be as cheap as iterating a linked list or an array. There's not a whole lot we can do without fundamentally changing the data structure we're using. To go as fast as possible, you want a simple data structure here. The choices being either a linked list or some sort of array. Now, in this particular case of just iterating the elements of the cell, both of these choices work, so you probably go with array since it's almost certainly faster. But data structure changes have a more global effect on the class, so we need to see how the insert and remove functions would be affected, given the choice of either data structure. So let's look at insert first. This is pretty simple. It gets the bounds of a client, iterates all cells that overlap it, and inserts the client into that cell. So either data structure works here. You can trivially push to an array or a linked list, nothing complicated about that, so let's move on. In the remove function, we do a similar looping through all cells, but there's a small gotcha here. In any given cell, we need to remove the client. Previously, these were set containers, which can do a lookup and find the item you're trying to delete in order login or even order one time. But if we change this into something other than a set, we need some way of deleting elements quickly. Finding and deleting a specific element from an array or a linked list, for example, is order n. It's slow as dirt. But there's a couple tricks here we can use that can speed things up considerably. With an array, finding an item is the bottleneck. But if you already know the index of an item, under certain conditions, this can be extremely fast. Consider this array. You could imagine these are items in your world, for example, and say here at this index, you want to remove this guy here. Normally, when you think of removing an item from an array, you have to do a somewhat complicated bit of surgery to the array. You take the item out, then you go and shift everything left by 1 so that everything is back in the same order, no gaps or anything, just missing the item you wanted removed. But here's where you can make it faster. If you don't give a crap about the order of the items, instead of shifting everything over, you can simply swap the item with the last item in the list and then pop it off the end. Job done, barely takes any time at all. Similarly, for a linked list, finding the item is the bottleneck, but given a node in a list, removing it is trivial. Let's use a doubly linked list as an example. You've got your pointers to the previous and next items in the chain, so removing an item is as simple as modifying the previous item in the chain and pointing it past you to the next item, and then doing the same for the next item in the chain, just pointing it to the one behind you. At that point, the item you wanted removed isn't referenced anywhere, effectively removing it from the list. Back to the code, so how does this help us? In the context of this delete function, it means that if the client had carried some extra information about exactly where it was in the list for any given cell, this delete function would be trivial. You might be able to get an array to work here, but I'm going to go with a doubly linked list for simplicity. So what we'll do is we'll need to make a handful of small changes throughout the class to change everything to use a doubly linked list. Starting with the constructor, we're not going to allocate a single map anymore. Instead, we're going to allocate a two-dimensional array of nodes, each one corresponding to a cell. And of course, since we haven't inserted anything into the grid yet, each cell will be initialized to null. This will take care of having to do any kind of checks to see whether or not a cell exists before we access it, since they all exist, even if they're just null. It's a bit of a trade-off, using a bit more memory, so you can decide if it's the way you want to go. Now, a new client, I'm going to change things a bit in the client dict. Instead of the indices, we're going to store a few more things. I'll change this to a full-on subdict, calling it cells, and it'll store the indices of the cells this client has been inserted into, which isn't much different than before. We'll also add this new field called nodes, and what this is going to do is, for any given cell, we can access the linked list node that was created to insert this client. Okay, so the initialization is out of the way. We just need to make some modifications to find nearby, insert, and delete to support the new linked list. Starting with find nearby, the old code used to use the XY cell indices to create a hash string to access the cells map, but we can just use X and Y directly to access the head node for that cell. At that point, it's just a simple matter of iterating the linked list. So while head is defined, we can access the client from the node's client property, and then we assign head to next. The inner part of this loop is identical to the old version, where we check the query ID and then insert it into the results array. Let's scroll down to the insert function now. This changes a little bit more. The first thing is that since insert is what's called to actually insert the client into each cell, we want to track the nodes. So we declare that at the top here, and in the first iteration of the x-axis, we just insert another array, making it two-dimensional. Now in the inner loop, this used to be a simple add call, but we're going to have to do a bit more work now. We define a dict called head, which is a node in the doubly linked list, and default the previous next pointers to null. At that point, we insert it into the nodes array, which is going to get saved on the client. Then we're going to set head.next to equal to the head of the cell's linked list, effectively making this the new head of the linked list. So you just set the current cell's previous node to head, and then you set the cell to point to head. At the end of the function, we just need to do a little maintenance on the client. So we need to fill out the cell's dict with indices and nodes. So that's all we're doing here. Okay, last up, we need to modify the remove function. So let's take a look in here. This was a relatively bare bones function before, since the setDelete function took care of everything for us. In the inner loop, we need to make a bunch of modifications, basically doing the doubly linked list removal for ourselves. So the first thing you want to do is get a reference to the linked list node, and we save that back in the insert function. You just need to access the client.cells.nodes with the proper indices. Removing from a doubly linked list is as simple as inserting. So what you need to do is look at the next node in the list, and if it exists, you have it reference the previous item in the chain. Same with the previous item. You need to check that exists, and if it does, assign its next to the next item in the list. Lastly, there's one final check that needs to be done, and that's if you're deleting the head node, because it's referenced by this .cells at x and y. So if you're deleting the head node, just make sure you update the reference there to point at the next one in the list. And that's it, we're done. It was a little involved, but if you're familiar with linked lists, this should have been a breeze. Let's test the performance out. So I won't bother with a profile, and I'll just reload, and let's check out the numbers. The first thing that pops out is the find near calls appear to be slightly slower, but that's not too unexpected. The major difference in find nearby is the use of a linked list instead of the built-in set type. So I could believe there's some heavy-duty optimization on V8's end of things to make the set container as fast as possible, faster than iterating our own hand-rolled linked list. The real changes come from the insert-delete functions. That's quite a bit faster. The time difference here is massive, around 2.5 to 3 times faster, so this is really substantial. Depending on the game and the usage patterns, this trade-off is probably easily worth it. And there's still room for more improvement and easy wins in there. Back in the code, let's scroll over to the update function. This is implemented in a super simple way. We simply remove the item from the grid, and then we reinsert it. Now you can try and do something more complicated, like figure out which indices it used to be in and which ones it should be in now and do a difference on the two, but let's think about the problem a bit. Let's start with a basic rectangular world, so I'll just draw a super crappy one. And then let's just throw some random crap in there real quick, so I'll add some people and monsters and whatever else. You can just endure me drawing some stuff. So if I overlay a grid on top, and now let's think about what's happening in any given frame. The game is likely to be running at something like 30 FPS minimum, meaning you get about a 30th of a second to do anything like movement and whatever else. Now, even if you're using small cells, 1/30th of a second isn't a whole lot of time. If this guy is walking across the field, they'll barely make it anywhere in any given frame update. Chances are that a few units will cross cell boundaries, but in reality most will just be in a slightly different spot in the same grid cell they were in before. Basically, we can expect a lot of temporal coherence between frames. Everything is mostly going to be in the same place it was in the previous frame. Back in the code, that means that we shouldn't reasonably expect that a given client will move far enough to trigger a full removal/insert. In fact, we can build in a check to see whether or not this has happened. So we look at the cell's indices this unit overlaps with and check whether or not they're the exact same ones that are stored in the client. We store the min-max indices, so you're just doing 4 equality checks here, and if they're all the same, we can early out and return from the function. Let's test out the performance here, which just means reloading the page. And the numbers are super promising. Again, no need to look at the find nearby numbers since there's no relevant changes there. But look at the update numbers now. These are awesome, down to just 20 milliseconds or so, at least in this synthetic benchmark. This is roughly 15 times faster than the original implementation and 5 times faster than the improved faster one. Now, our synthetic benchmark only allowed a small bit of movement to kind of simulate an individual unit moving around on a map. But depending on the size of your cells or how fast or frequently things move around, you may be hitting that slower remove-insert path more often. So both optimizations could be necessary. For fun, we can take a quick profile, so I just head over to the Performance tab, clear out the existing profile, and hit the Reload button. I want to capture a solid couple seconds of time before hitting stop, and then I can poke around. There's always more things you can do. Like in this case, I'm scrolling through the graph here, and you can see there's quite a few GCs, or garbage collections, being triggered. There may be some wins to be had by creating our own allocators and reusing objects heavily. I can also go poke around in the Sources tab to see what else is available. But in reality, here's where we can kind of leave things. I just wanted to give you a step-by-step idea of what I might do when I'm profiling, and we've been able to take this initial spatial grid implementation and make it considerably faster, given just a few half-assed passes to make it do less stupid things. Hope you enjoyed this and learned something in the process. Code should all be up on GitHub, like I sometimes remember to do. Let me know what you thought in the comments. Also, remember to like and subscribe, and until next time, cheers.